Good morning, and welcome to the third of three videos on section 12.2 in your textbook entitled Evaluating Limits. Whoops, what is going on? In this video, we are going to actually look at what's called the existence of a limit, okay? And so if the way that we have to define this is as follows. If f is a function, okay, and c and l are real numbers, c being the value that x is approaching and l being the actual limit, okay, then the limit as x approaches c of f of x equals l. But this is true if and only if both the left and the right limits exist and are equal to L. Okay, so as we discussed in the last video, if you approach a value of x from the left and another value of and a value of x from the right at the same time, first, both of those limits have to exist and they have to be the same in order for the limit as a whole to exist. All right. If they approach different, if the value of y is different as you approach x from the left and x from the right, then the limit does not exist. All right. So again, probably the most practical way to look at this is to actually examine an example problem. So let's have a look. All right. In this case, we're asked to find the limit of f of x as x approaches 1 of the function f of x equals 4 minus x if x is less than 1, and 4x minus x squared if x is greater than 1. Now, if you know or remember anything about your graphing, you'll know that these two functions, f of x equals 4 minus x and f of x equals 4x minus x squared, have very different shapes. The first one, the top one, is a line, all right, with a slope of -1 and a y-intercept of 4. The bottom one is an inverted parabola, all right, so an upside-down U shape, okay? But that doesn't mean that the limit doesn't exist just because we're dealing with two different functions. So the way that we're going to approach this is as follows. We're going to look, come on, please, the limit as x approaches 1, and we'll start with the left. So the limit, that's what the negative sign here means, of 4 minus x. Okay, so in this case, as we approach x equals as x approaches 1, if we plug in a 1 for the value of a value of 1 for a value of 1 for x, 4 minus 1 gives us a limit of 3. Okay. Now, on the other hand, if we take the limit as x approaches 1 from the right side, and again, that's what the positive sign here means, we've got 4x minus x squared. Okay, so if x is equal to 1, then 4 times 1 is 4. X squared is 1 squared, or 1. So 4 minus 1, again, gives me 3. So does this limit exist? You bet your sweet bippy it does. All right. We approach 3 as x approaches 1 from both sides. And so this limit does indeed exist. Now, we can demonstrate this graphically as well, although I warn you that the graph is a little odd looking. Let me change color here, and I'll change it to black. Here is the value of x equals 1. So this is really the line that we're looking at. All right, this is the point. And notice this is y equals 3. But you because Graph sketch does not allow me to eliminate the lines, but this should not be here, okay? Nor should this be here. All right, so just imagine that these two parts of the line don't exist. And so in this case, what we really have is a function that looks like this until we reach x equals 1, and then looks like this. Obviously, I'm not writing right over the line, but when x is greater than 1, okay? And so that's what the graph of this would actually look like. If you look at the green line or the green curve, that's what the limit or the function should look like. But notice that both from the left and from the right, in this particular case, and I'll do this in cyan. I don't know what cyan is, but we'll pretend. As we approach, that's cyan. As we approach x equals 1 from the left, we approach y equals 3. As we approach x equals 1 from the right, we approach y equals 3. All right, and so in both cases, we're approaching the same value, and therefore the limit of this function does indeed exist. Okay, let's look at another example. All right, this also is a piecewise function, but notice there's no equation here. It's simply a matter of constant numbers here. So to ship a package overnight, a delivery service charges $24 for the first pound and $4 for each additional pound or portion of a pound. Let x represent the weight of the package, and let f of x represent the shipping cost. All right, show that the limit of f of x as x approaches 2 does not exist. Okay, so in this particular case, we know that the standard shipping charge is 24 bucks. All right, and so if the weight is anywhere between 0 and 1 pounds, it's going to cost you $24 to ship it. If it's anywhere from 1 to 2 pounds, it's going to cost you 28 bucks to ship it. And if it's anywhere from 2 to 3 pounds, it's going to cost you $32 to ship this thing. Now, this is a what we call a stepwise function here. And so if we just look at this, because there's no arithmetic to do, we're just going to graph it. And so what the graph in this case is going to look like is this. All right. If the value of x is 0, if the value of x is 0, it's not going to cost you any money. But anywhere from 0 to 1 pound is going to cost you $24. So this is 24. Now I'm violating my principal rule because I'm breaking the axis here. Right? This box is going to be worth 24, but this box is going to represent $28, and this one is going to be worth $32. Now, so if the package is 1 pound, it's going to cost you $24 to ship. But if the package is 1.00000000001 pounds, right, just a fraction over 1 pound, it's going to then cost you $2. Okay, so 1 pound, if x equals 1, it's going to cost you 24. But any fraction over 1 is going to be 28. The same thing goes for the difference between 2 and 3 pounds. All right. And so if it's 2 pounds, it's going to cost you exactly $28. If it's any fraction above 2 pounds, it's going to cost you $32. All right. And so this is what we call a stepwise function. But most importantly, for the question that we're asking here, in this particular case, we're asked as x approaches 2 from the left. All right, the limit is $28. But as x approaches 2 from the right, the limit is $32, okay? And so the limit as x approaches 2 from the left of f of x equals $28, okay? The limit, on the other hand, as x approaches 2 from the right of f of x is $32. Because these two limits are different, the actual limit does not exist. And you can abbreviate that as DNE for does not exist. Okay? All right. So that is that. All right. So we've given you an example of a limit that does exist and a limit that does not exist based on approaching a value of x from both the left and the right side. Now, last thing that I want to cover in this section is limits from calculus. You may remember from chapter 1, we talked about the idea of the difference quotient, all right? In the next example, we'll look at the difference quotient. And so the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, that was the difference quotient here. Now, let's look at an example of this. So let's take the function f of x equals x squared minus 1. Okay, so we're going to be asked now to find the limit as h approaches 0 of 3 plus h minus f of 3 all over h. So how do we plug this all in? Well, this becomes the limit as h approaches 0 of, and now in this case, I'm going to use some brackets here, and this is going to be 3 plus h quantity squared, right? Because 3 plus h represents the x, right? Minus 1 minus, now f of 3 is going to be, in this case, 3 squared, right? Because 3 represents the x, minus 1. And that's going to be all over h. Okay. Now take a minute and actually look at that. We're using 3 plus h as the x value and 3 as the x value in our functions. Okay. Now I'm going to come up here and just do the math out here. The first thing I have to do is square 3 plus h. Okay. So using the FOIL method, that's going to give me 9, right? Because 3 times 3 is 9, plus 3h plus 3h, right? The outer and the inner is 6h. And the last, which is going to be h squared. Okay, minus 1. And then on the other side, 3 squared is 9, but notice the negative sign here. So it's going to be minus 9, and then minus 1. But again, there's a negative sign, so that becomes a positive 1. Again, all over h. Now, this actually simplifies, and I forgot the limit notation, but it's the limit as h approaches 0. Now, the next step is to simplify this a bit. And if you look at the numbers carefully, you'll see the 9 and the -9 cancel out, and the -1 and the +1 cancel out. And so I'm left here with the idea of the limit as h approaches 0 of 6h plus h squared all over h. Now I can simplify this further because I can cancel an h out of each of the terms. And so this becomes the limit as h approaches 0 of 6 plus h, right? Because I can get rid of the h here.
It's 9 o'clock.
Thank you, Jesus. The square here and the h here, right? They all become 1. And so I'm left with the limit as h approaches 0 of 6 plus h. Well, now, if h approaches 0, then this is simply going to equal 6. And so my limit in this case is 6. All right? So there's the how you would calculate a difference quotient in this particular case. All right. So that, my friends, brings us to the end of section 12.2. And so your assignment for next time is to do the homework questions 5 through 41 and 47 through 50. Again, odd numbers only, okay? Notice you're going to skip numbers 43 and 45, all right? All right, boys and girls, that is all I have for you today, and I hope you learned something.